Okay, so we define self-adjoint linear operator. Alright, so here, a linear operator on a finite dimension linear product space V is called self-adjoint if its adjoint is equal to T itself. So that's simple, right? The T dagger is equal to T. In this case, we have this crucial property that T of x inner product with y is equal to x inner product with T of y. So you can move T here from here to there without affect the result. Right? So that is the crucial property of self-adjoint linear operator. And correspondingly, n times n matrix complex matrix A is called permission or self-adjoint. Right? If A permission transpose is equal to A. And in this case, y h a x is equal to y h a h x for all x y in Cn. Okay. So of course this is true, right? This must be true because A h equal to A. Okay, h equal to A. Right. So now we will give a theorem to characterize self-adjoint linear operator. It's 8.1.2. 8.1.2 plus 3. So we put two theorems together. So let T be a self-adjoint linear operator on a finite dimensional inner product space V. Then we have two consequences. Every eigenvalue of T is real. Second, if U and V are eigenvectors of T corresponding to distinct eigenvalue eigenvalue lambda and mu. Then you found out this. Okay, so we have two consequences. For any self-adjoint linear operator on a finite dimensional inner product space, so we let 3 be an eigenvector of T corresponding to eigenvalue lambda. Right? And we want to prove lambda is a real number. Right? So then we look at TV, V. Right? So T operates on V, and inner product with V itself is equal to V and the TV. Right? Because T is self-adjoint. So this one, and this says that this is a lambda V. V is equal to V lambda V. Okay? Because V is an eigenvector corresponding to eigenvalue lambda. Now we have lambda. Okay? So by the linearity for the first argument, right, of the inner product, we have that. And for the second argument, we have conjugated linearity. So we have the lambda bar. Okay? And this is lambda equal to lambda bar. Since is positive. Okay? Because eigenvalue should be non-zero. Right? Eigenvector should be non-zero. So that lambda is real. Okay, so we have the result. So for any self-adjoint linear operator, every eigenvalue is real. Okay, so this is the first part. Let's see the second part. Now, let U be an eigenvector of T corresponding to eigenvalue mu not equal to lambda, right? So we let U. So we have an eigenvalue lambda and there, and consider U be an eigenvector of T corresponding to eigenvalue mu, and mu is not equal to lambda. Okay, and so T U V is equal to U T V, right? And this implies that this is mu U. And this is the mu lambda V free. Okay, and the lambda is here. Now, you may think about why when we move the lambda out of the inner product and not put the complete conjugate. Because we just proved that any eigenvalue of a self-adjoint operator is real. Alright, so since lambda is real. Okay, so we have that. And this is implies mu lambda u v equal to 0. Alright, and so this is implies that thing okay, so that u is orthogonal to v. Okay, so we have that. Okay, so eigenvectors corresponding to distinct eigenvalues are orthogonal to each other. Any questions? All right. Okay, so we have some consequences. X p from Cn to Cn with Px equal to Ax where A is an n times n complex matrix. Okay, then P is self-adjoint. We can only A is Hermitian. And the proof is that this follows from the example above. So last Wednesday, I took an example to demonstrate for a linear operator constructed by an n times n complex matrices. Its dagger is equal to the dagger. D dagger is AHA, right? Corresponding to the Hermitian transport of A. So that if T is self-adjoint, of course, that A is equal to AH. Okay, so this is easy. Okay. Because it's a theorem in the textbook, so I write it for you here. So basically, this is from our discussion before. And 8.1 plus 2, all eigenvalues of the Hermitian of a complex matrix are real. Okay? So if we have a Hermitian complex matrix, then we can construct a self-adjoint operator by this way. And from the previous theorem, any eigenvalue of a self-adjoint operator has real eigenvalues. Okay. And we know the eigenvalue of T is equal to the eigenvalue of A. Okay. We discussed that before in chapter 6. So that for a Hermitian complex matrix, all its eigenvalues are real. And similarly, all eigenvalues of a symmetric real matrix. Okay. When regarded as a complex matrix real, also real. So if we have a symmetric real matrix, because for a symmetric real matrix, when we regard it as a complex matrix, then that is also Hermitian. Okay, it's also Hermitian. And then all eigenvalues are real. The reason why I put this word is that, as we discussed before, if you are given a real biomatrix, this matrix may not have any real eigenvalue. Okay? May not have any real eigenvalue. But for any complex matrix, you must have at least one complex eigenvalue. Okay? Why? Because that by the fundamental theorem of algebra, all complex coefficient polynomial has solutions. We can split complex polynomial into linear vectors. So this is the fundamental theorem of algebra, proved by Gauss several centuries before. Okay, so any complex matrix will have eigenvalues. So you can regard a real matrix as a complex matrix, and then you will have a complex eigenvalues, of course. But for symmetric real matrix, if the matrix is symmetric matrix means that A is equal to A transpose. Hermitian means A equal to A. Okay? So symmetric means A equal to A transpose. So this implies that A equal to A Hermitian. Okay? Because A is real. So if you put the conjugate, you will not affect anything. Okay. So that all eigenvalues of these two types of matrices are real. Any questions? Okay, so if no questions, then I will start to develop the spectral theorem for you. First of all, I'll give you a lemma. So let T be a linear operator. Okay? On an n-dimensional inner product space. V over F. So F can be R or C. Right? So we consider a linear operator on an n-dimensional inner product V over either the real number field or the complex number field. Now, let's U1, U2 up to UN be and also normal basis for V. Okay, so now we have an orthogonal basis. Then each UI is an eigenvector of T corresponding to eigenvalue lambda I in F in F. Very important in F. So if we are considering real inner product space, then eigenvalue should be real. Okay? Then I have to emphasize F. For all I from 1 to n, where lambda I may not be cannot be all distinct. Okay, so each UI is an eigenvector of T corresponding to eigenvalue lambda I in the same scale field for all I from 1 to n, and of course the lambda i's may not be all distinct. Right, so this is true if and only if okay, so this statement is true if and only if the linear operator can be written in this simple way. What kind of way? Lambda I inner product of X with UI and UI. Okay? Very simple, right? So this is called a spectral decomposition. We can decompose the linear operator into sum. Okay? And this is very simple expression. Okay? So of course, in this case, this also normal basis is an eigenbasis. Okay, because that each vector in this basis is an eigenvector of T corresponding to eigenvalue lambda I in the same scalar field. Okay, so the lemma tells us that we have such a simple decomposition for the linear operator. If and only if we can find an also normal eigenbasis for the V. Okay, so we can find a full eigenbasis. And we have give us necessary sufficient condition for such eigenbasis to exist in chapter 6. Okay. Alright, so we give a proof. Right, so the direction. Suppose we have an orthonormal eigenbasis. Okay. Now, for each vector in the inner polar space, we have that x is equal to, so because this is a basis, an orthonormal basis, right? So that it can be, x can be represented as a linear combination of u1, u2 up to un, and the coefficient can be determined easily. It's x, ui. So the coefficient is just the inner product of x and ui. Okay. So basically, this is the projection. Remember, this is the projection of x onto ui. The projection only y, because that the projection is here. So this one is the projection of x onto ui. The projection. But because it's also normal, so each u1 is a unit vector. So the denominator is equal to 1. Is equal to 1, so you don't need to write it. Okay? Because this is 1. So that's why we can simplify it. Okay? So let me do it. So this is okay, as a remark here, to let you know that this one is just a projection of the vector onto ui. Okay, and we add up all the projections together and give us the original x. Okay? Alright, so we have this one, and then we'll apply the linear operator x on x. So we have okay, and by linearity we have the I here. And because ui is an eigenvector of t corresponding to eigenvector lambda I, so now we have 1 lambda. Okay, so we have that. Alright, so if ui is an eigenvector of t corresponding to eigenvalue lambda I, then we have this decomposition. So Tx is like that. Okay, now the reverse direction. First of all, since T uj, suppose this is true. Now we let x to be uj is equal to summation I from 1 to n lambda I uj ui ui. Okay, and because they are also normal, so that if I not equal to j, this is 0. But for I equal to j, the inner product is equal to 1. So So we have number j with that. Since okay, so so here uj is an eigenvector of T corresponding to eigenvalue number j for all 1j from 1 to n. Right. All right. So immediately we know that each u j is an eigenvector corresponding to, and so we have done. So this is a simple lemma. Okay. So it just gives you that if we want to have such a simple decomposition, if and only that you should find and also normal eigenbasis for the V. Okay, you should find an also normal eigenbasis. Okay. So now we will see some consequences. The decomposition here. So assume that we have the decomposition Tx equal to summation n from 1 to n number I x ui. Where u1, u2, un is an also normal basis for an n-dimensional inner product space. Okay? So suppose we have a linear operator, and the linear operator can be expressed in this way, and such that u1, u2 up to un is an also normal basis for V. Okay, so now think if this is true, okay? If this is true. Now think right? So we look at this inner product, Tx1, summation lambda I y here. So by linearity for the first argument, so we have lambda I ui1 here. And so we have two rules. Alright, if the scale field F is real, the scale field is real, then alright, so we will have Okay. So this is x summation I from 1 to n of the I y and okay. If we exchange them, we will have okay, and see. Okay. So we now binarity of the second argument. This is the scalar, so you can move into it, and scalar move into there, and the sum into there. So you put everything into the second argument. Okay, and leave x here. And you can exchange the order of inner product, because in the real case, now you don't need to put the complex conjugate with everything in real. So when you exchange them, okay, without changing anything. But if you, in the complex case, if you want to move into here, you have to exchange. Because that, because if, when you move into that, you have to put the complex conjugate there. So that this one is the complex conjugate of this one. Okay? Alright, so this, what is that? This shows that because that and this one is equal to x d dagger 1. Okay? So dxy is equal to x d dagger 1. So from here, the adjoint d dagger of t is for all x in V, the t dagger x is equal to summation I from 1 to n lambda I x ui if f is equal to r. The other is 1 to n lambda I is bar x ui if f is equal to c. Okay, so here, this one, okay, so you have this. And but if we have a complex conjugate, if we will allow consider a complex case, you have to put the complex conjugate for the eigenvalue of lambda I, because lambda I in general is complex. Okay. So in particular, when the scalars are reals, we have t dagger equal to t, i.e. t is self joint. Aha. So if we have this spherical decomposition, if we have this decomposition, then if the scale field is a real number, is real, then the linear operator should be a self-adjoint linear operator. So this is a necessary condition. Alright, so this is for real case. We now consider the case of f equal to the set of all complex numbers. Now, for j from 1 to n, we have t dagger uj lambda I bar uj ui ui. So what is that? This is lambda j bar uj. So which shows that uj is an eigenvector of t dagger corresponding to eigenvalue lambda j bar. Okay. So if we have this spectral decomposition, so if T has a spectral decomposition, okay, so this is good. Okay. So if T has a spectral composition, then we say that for the complex case, that is a joint T dagger, right? For the joint, we find that the same eigenvector, because uj is an eigenvector of T corresponding to eigenvalue lambda I. And the same uj becomes to an eigenvector of T dagger corresponding to eigenvalue lambda j bar. So the eigenvalues of T dagger are the complex conjugate of eigenvalues of T when T has a spectral composition. So this is very important. You have the premises here. This is the requirement. T has. So if T has no spectral composition, we can't have this property. Okay? So it's very important to know that if T has spectral composition, then for the real case, T must be self-adjoint. For the complex case, the dagger, T dagger, has eigenvalue which are complex conjugate of eigenvalue of T, and they share the same eigenvectors. Okay. So now we have for all x in V, we look at the composition of t and t dagger. So t dagger x. Okay? So this is t dagger, tx. Alright, so what is that? This is I from 1 to n. So t dagger, so we have lambda I and x ui find the spectral decomposition because Tx satisfies this spectral decomposition. Right? And find the linearity of T dagger, because T dagger is linear. So we have ui, T dagger ui here. But ui is an eigenvector of T dagger corresponding to eigenvalue lambda I bar. So we have lambda I ui. Okay, and so we have lambda I bar ui t ui. Okay, t ui here because ui and together this is t ui. Because ui is an eigenvector of t corresponding to eigenvalue lambda I. Okay, and by linearity of inner operator by analogy, here okay, and the T dagger, so this is T dagger of x. Remember the definition here, T dagger is this one. So it has a spectral decomposition. Alright. So this is the spectral decomposition of T dagger. And so this is T dagger x. So we find that the composition of T dagger and T can exchange the order. Okay? Can exchange the order so that they are commute. So we have that T dagger composed with T equal to T composed with T dagger. Okay? So for when f equal to r, we have this one. So if we are considering real scalars, real case, then the linear operator T, if T has spectral condition, then T must be self-adjoint. But when the case, for the complex case, that we must have this property, T dagger composed with T equal to T composed with T dagger. Right? So now, so a linear operator to give a name. A linear operator T on an n-dimensional inner product space. V over C is called normal if T commute with its adjoint, i.e. T dagger, T equals T dagger. Okay. So any operator have this property is called normal. Okay, so they are called normal operators. Alright, so example. So let V is just our n-dimensional Euclidean complex Euclidean space, and Tx is equal to Ax for all x in Cn for some n times n complex matrix A. Now the adjoint of T, the adjoint T star of T is T dagger X is equal to AH X, as we know, right? So the dagger, T dagger, is that AH X for all. So then T is normal. So T is normal if and only if T dagger equal to A equal to T dagger X, which is AH X. Okay? So if and only if AHA equal to AH. Okay? Right, so if we consider linear operator on Cn by using an n times n complex matrix A, then this T is normal if and only if AHA equal to AH. And because of this reason, a complex matrix A is called normal, right? If AHA equal to AH means that A is commutative with its Hermitian transpose. Okay, so let's take a short break for 5 minutes. We will answer the question. When a linear operator T, right? When does the linear operator T on an n n-dimensional inner product space. Have spectral decomposition. Okay, so the question, we have to answer the question. Alright, so it's very nice if we have a linear operator which has a spectral decomposition. Because that to find the function value, we just do the important thing is to do the inner product only. Okay? Alright, so that so we should characterize Rho's linear operator have spectral decomposition. Okay, and we have partial answer. We have just shown that what if f equal to r. Okay, so the case, case 1, f equal to r, if t has spectral decomposition, then T must be self-adjoint. Okay? So T must be self-adjoint means that this is a necessary condition. And we have case 2. And f equal to c. If T has a spectral decomposition, I forgot to and lambda I s. So the scalar must be in the same on the same scale field. Okay, I forgot to put. Okay. So if we are talking about real inner product space, then everything should be real. Okay. And if we are considering complex case, then of course everything can be complex. So now for the complex case, if T has spectral decomposition, then T must be normal. It must be normal. Normal is more general than self-adjoint. Why? Because that if T is a self-adjoint, then T dagger is equal to T. So it must satisfy, because T is T, right? T comes to T equals T comes to T, right? So self-adjoint implies that it's normal. But normal may not be self-adjoint. Okay? So for the complex case, that this necessary condition is wider. Is wider. For the real case, he must be self-adjoint. Okay? He must be self-adjoint. Now, So we just show that we have necessary conditions. Okay? Now we will show that this necessary condition are also sufficient in the respective case. Okay? So for real case, if T is stable joint, then T has a structure of linear. We have to show that. And if for the complex case, if a linear operator is normal, then T has a structural condition. So we have to prove the reverse direction, and that is a little bit non-trivial. Okay? And we will work on the complex case first. All right, so now, okay, so I try my best because I'm afraid of that the time is not enough for me to develop the whole theory. Okay, a linear operator T on an inner product space V over F is called invariant on a subspace W of V if T W is in W for all W in W. Okay, so the image for every vector in the subspace, the image is also in the same subspace. If this is true, then W is called invariant. Okay? It's called invariant. So T is invariant on W. Now in this case, the restriction T restriction of T of W denoted as T restriction W is a linear operator on W. Okay. Okay, so 8.1.C, all right, this is called a complex spectra theorem. All right, so let T be a linear operator on an n-dimensional inner product space V product space over C. Okay, so it's complex inner product space. They are complex numbers under 1 and 2 up to lambda n not necessarily distinct. And also normal basis U1, U2 up to UN for V such that Ex equal to summation I from 1 to n lambda I x ui for all x in V. Alright, so this happens if and only T is normal. Okay, so this is the complexity spectral theorem. The proof, the forward direction, this is done in above. Okay, so we have done the forward direction. So now we will prove the reverse direction. So we let T be a normal operator right? So the starting point is that T is a normal operator. This is the starting point. Now we will show. So we will show that there are complex numbers number 1, number 2, number n, not necessarily distinct. And also normal basis U1, U2 up to UN for V such that T x equal to summation I from 1 to n lambda I x u I for all x in V. So we will show that by induction, right? On what? On the dimension of V. Okay? Wow. That is too crowded. So okay, maybe I put here by induction on n, which is the dimension of V. Okay, so we'll show that dimensionally. Okay. Oh, by the way, our final examination will be next Wednesday morning from 10 o'clock to 12:20, and the coverage basically the whole book, okay, up to section April 1. Okay, so now because we have to show it by induction. So now for n equal to 1. So if the dimension of V is 1, so the dimension of V is 1, alright, so that U1 be an orthonormal basis for V. Now, since PU is in V, so there exists a complex number I think just U. Sorry, we don't need index. PU, U is an orthonormal basis. So there is a complex number lambda such that PU must be equal to lambda U. Because it's one dimensional. So the image should be a multiple of U, because it's the basis. Okay? Now, since x is equal to x u u for all x in V, so we have dx equal to t. So this is equal to lambda x u. Okay, and the tu is lambda u, so we have this one. Okay, so you can see that what we want is that we can find complex number, number 1, number 2. For n equal to 1, we should find a complex number lambda, and an orthonormal basis u, alright, such that we have this expression. And we have done, right? Because we have found an orthonormal basis, and we find a complex number lambda. Okay, and Tx can be expressed in this one. Only one term, because the dimension n is equal to 1. Okay, so we have done, so that, okay, so this is equation 1, okay. So 1 is true for n equal to 1. Okay, and now we assume an induction step. So assume that 1 is true. Okay, for n equal to 1 to up to k, with k greater than 1. So maybe some k greater than 1. Of course, when k equal to 1, this is fine, right? We just prove the starting point. And so we assume that the one, this thing is true for n from 1 to up to k. So now consider the case of n equal to k plus 1. Okay? So now the dimension of the inner product space V is k plus 1. Now, since the characteristic polynomial of T factorized to linear factors. As we know from the fundamental theorem of algebra, any polynomials of complex coefficient can be factorized into linear vectors. Okay? So that over C, of course, over C. So T has at least one eigenvalue, lambda. Okay? So T has at least one eigenvalue, lambda. Alright, so let E be the eigenspace corresponding to eigenvalue lambda. Okay? Now T is clearly invariant on E. Why? You know why? Think T x equals to lambda x for all x in E. Right? So if x is in E, then the image is the multiple of x, of course, because eigenspace is a subspace, so that Tx is also in E. So maybe, right. So E is a nature invariant subspace. So now for any U in E, right? So we consider any U in E. So we have now T compose T dagger U, okay, which is T dagger U, okay, and it's equal to T dagger, so T U, okay, and what is this? This is T dagger T U, okay, so this is T dagger lambda U. So that from normality, because we assume T is normal, so T dagger, T composed with T dagger is equal to T dagger times T. Now from here, what is this? This one is T dagger U. Okay? Okay, so that we have T on T dagger U is equal to lambda T dagger U. So which implies that T dagger, this image is in the eigenspace. Okay? Must be in the eigenspace. And then T dagger is invariant again on E2. Okay? So T is invariant on E, and we just show that T dagger is also invariant on E. Okay? And T dagger is invariant on E because T is normal. We will use the normality here. We give us know that T dagger is invariant on E. So now let E curve be the orthogonal complement with an orthogonal complement of E. Now, for any V in the orthogonal complement of E, we have, so we see that TU, TV, U, right? So the image of V, remember V is in the orthogonal complement of E. So T on V, and take the inner product. Now, this is T dagger U. Okay? And we just show that T dagger U for all U, so that so this is 0 for all U in E. Okay? So now V is in T dagger, and any U in E, maybe I say here. Okay? So for any V in the E dagger, E perp, and U is in the eigenspace corresponding eigenvalue lambda. So we have TU, TVU, this one, and because this one is in E, as we just showed, T dagger is invariant on E, so that the image is also in E. And so V is in E perp, and this vector is in E, so of course they are orthogonal from 0. And similarly, T dagger V U equal to V T U. Okay? And this is also 0 because this is also in E. Because T is invariant on E. So this vector, this image is also in E. Okay, so they are orthogonal. Alright, so now which implies that, so this is true, this is, so the image of V under T orthogonal to all U in E. The image of V under T dagger is also orthogonal to all U in E. So this implies that TV is in the E perp, and T dagger V is also in the E perp. Okay? So that both T and the T dagger are invariant E perp. Alright, remember, V is in E perp, and we find that TV is also in E perp. T dagger V is also in E perp. So T and T dagger are invariant on E perp. And the restriction T on E perp and T dagger on E perp of T and the T dagger on E perp are linear operator on E perp. Okay? So they are on E perp. So we consider restriction of the original t and t dagger on the E curve. Okay, so also for all VW in E curve, we have P E, the restriction on VW, which is equal to T V same, right? So the operation on that same, and this is equal to V dagger W, and this is V dagger operate on W. That's it. Okay, so from this relation, so that T dagger restrict to E curve is just the adjoint of T restrict to E curve. Okay. So not only T dagger is the adjoint of T on V, but also the restriction of T dagger on E curve is just a subspace of V, is also the adjoint of T restrict to E curve. And since T dagger, because T is normal, so we have restriction to E curve. So this is T dagger, E curve, T E curve. And so this is equal to T dagger, E curve, and so this is T so which shows that T E curve is a normal operator on E curve. Okay. So we show that this restriction is a normal operator on E curve. Now, since the dimension M of this E curve is the dimension of V minus the dimension of E. Okay? So that the dimension of, but the dimension so this is less than equal to K plus 1 and minus 1. Because the dimension of V is K plus 1. But the dimension of E is at least 1. Okay, at least 1. Because it's a null space. Right, so at least 1, and so the bound is K. Alright, so the dimension of E curve is K. But by our induction that E1 is true for n equal to 1, 2, 3 up to K. So if the dimension is less than or equal to K, then 1 is true. Okay? So that 1 is true. I.e., there are complex numbers lambda 1, lambda 2 up to lambda n. And also normal spaces U1, U2 up to UM for the E curve, such that for all V in the E curve, the reflection of T on E curve operated on V is equal to summation I from 1 to M and the lambda I V UI. Okay, because 1 is true. So we have so T, the restriction of T on E curve has a spectral composition. Okay, this is from the induction step. Now, we let UN plus 1 up to UN be an also normal basis for the eigenspace E. Now, for any U in the eigenspace E, we have U equal to summation I from n plus, oh, this is k plus 1, I'm sorry. N plus 1 to k plus 1. Yep. And U, UI. Okay. Because that our dimension of V is k plus 1. Okay, so we have for any U in the eigenspace, we can have this decomposition. Now, since V is the direct sum of E and E curve, okay? Alright, so we know that before. There is a direct sum. Right. We consider in section 7.1, so that this direct sum for any x in the original vector space V, they are unique. They are unique V in the E curve and U in the eigenspace E such that x is equal to V plus E. So that's the meaning of direct sum. That every vector x can be formed by the sum of a vector in E curve and a vector in U. And the choice of V and U are unique. Okay, this is the meaning of direct sum. So that, and then Tx is equal to Tv plus Tu. Okay? And this is T restriction of T curve V. Okay? Plus I from M plus 1 to K plus 1 and UI, UI, T, UI. Okay? So Tu, because U has it's a linear combination of UI, I from M plus 1 to K plus 1, because this is the basis. And so by linearity, so if we put, because U here Okay? So by linearity, we get this one, because the coefficient move out of the t. And this one, because that t has a spectral composition already. Okay? So we have spectral composition. Okay, so we have over here. So here is summation I from 1 to m lambda I, and v ui plus summation I from m plus 1 to k plus 1. But ui is in the eigenspace, so we have lambda ui and ui. Okay, so we have this one. Now, for I from 1 to n, we have, so we look at here, x ui, the projection. Alright, so x inner product with ui, I from 1 to n. So that means that we have v ui plus ui. And what is that? U is in eigenspace E. Okay, it's in the eigenspace E. But ui, they are in the perp of E. So they are. So this is equal to 0. Right. So this is ui. So when I is from 1 to m, that the x inner product with ui the same as v inner product with ui. And similarly, for I from m plus 1 up to k plus 1, we have x ui, which is v ui plus ui. But the ui, when I from m plus 1 to k plus 1, they are in E. So, but v is in E perp. Okay, so this is 0. And now, so we have ui. So that means that for I from 1 to n, this inner product is equal to x ui. And similarly, for I from m plus 1 to k plus 1, this inner product is equal to x ui. Okay, so the construction is that alright, so by dating lambda m plus 1 equal to lambda k plus 1 equal to n to lambda. Okay, so that's why lambda i's may not be distinct. So we have Px equal to summation I from 1 to k plus 1, and the lambda I x ui together. So we can combine them together, because that the form here is x ui and this is x ui same. So and ui up to um plus 1 up to uk plus 1 is an orthonormal basis for V. Okay, so that one is true for n equal to k plus 1. So now we prove that for one is true for k plus 1. And so by induction, 1 is true for all n greater than equal to 1. And we have that. Come split up here. Okay, so the idea, let me draw the graph. V is here, E is here, it's not like this. So maybe I have to this is E. This is E dagger. Here. Okay, B is there. So every x, so that so we have say U, V, and x is V plus U. Okay. And so that the t respect to E, t respect to t dagger. So t respect to E perp and the t dagger respect to E perp are linear operators on the subspace. So we have use some effort to show that the t and the t dagger are invariant on E perp, and then these two are adjoined to each other. Okay, and then the t restriction to E perp also normal. So everything is perfect. And then because the dimension of E perp is smaller dimension of V. All right, so that this is t restriction to E perp is a spectral condition. And here, so that's the idea. We have spectral condition. Okay. And the other thing, so that we use the direct sum, because every x is a direct sum. A vector from the E perp and another vector U from the eigenspace. All right, and so now we can have this, and because all the vector here in this is in the eigenspace, so they are all eigenvectors. They are eigenvectors corresponding eigenvalue lambda. All right, so we have this expression. But to combine them together, we have to show this inner product is actually this inner product. And this inner product is also this inner product. And now we are able to combine them together into one. And this is just the spectral composition of the T of B. Okay. So the process actually give you a rigorous proof is because that we have to check everything to work on E perp. Okay? To work on E perp. So that we can use induction. We can use induction. Okay, so now we have induction here. By induction step, and then we add some point here to get our final dimension here. So that is the proof of the complex spectra theorem. Okay, and I think I have run out of time. So so that I will not be able to cover the real case. Okay. And the real case need the help from the complex spectral theory. Right? So this is important to establish that one. Okay, so I have to stop here, and for the rest of the material, I will send you lecture notes for you to read. Okay, so and all the applications that you can read over the textbook in section 8.1. Okay, and so well, anyway, I have to stop. Okay, and thank you for attending the class in this semester, and I wish you good luck in the final examination. So see you next week.